Okay, so in the last lecture, we started with velocity kinematics, and in this lecture, we will continue and hopefully we will complete it. So, in the last lecture, early I told you that this is the notation we use. In a frame B, if the position of a point Q is known, then that known position in that basis is expressed like this, and that can be converted, that vector can be converted to another frame by the rotation transformation. And for velocity of Q in frame B, whatever is that vector, when you try to convert that to A, then you denote it like this. So the sense is that in frame B, we have the direct description of a point Q and that of a frame of reference C. We want their motion as described in another frame, frame A. And for that, this is what we have if the motion is required in the basis of B itself. Okay, then we describe it as this, simply condensing the double superscript. Now, velocity of point Q, the motion of which is directly known already in hand in frame B, we want its motion in frame A. So there are two things here. One is the motion that is known in frame B is known in its basis, that has to be converted, and the motion has to be now in frame A, means relative velocity of frame B with respect to frame A also has to be incorporated. Okay, so this is the velocity of the origin of frame B relative to A as expressed in frame A, plus the velocity of point Q in frame B itself, and that will be counted from origin of that frame, and that converted to the basis of frame A. Plus, if the frame B has an angular motion, then that angular velocity cross the position converted to the proper basis, because only after both the vectors are in the same basis you can take a cross product which will be sensible. And this is already in frame A because it is basically this, in which the vector d omega B is the angular velocity of B in the basis B itself. Okay. Then angular velocity of frame C referred to frame A, that will be angular velocity of frame C in B, which is known, converted to the basis of A, plus the relative velocity of frame B itself, relative angular velocity of frame B itself, because that may be rotating relative to frame A. So in absolute frame, everything we denote by small letters like this, which is in the absolute frame U, which is basically the base frame for our purpose. That is frame GU. Now, with these management of the frames, we can now describe the motion of a point which is already available in one frame in the other frame, and motion known in a frame ahead in the manipulator we typically express in a frame which is behind. Okay, so I omega I plus 1, that means the angular velocity of frame I plus 1 in I. So that is, see, we are using here all small letters, small omega, small v on the left hand side, and that means we are talking about their actual linear and angular velocities absolute. So whatever is the absolute angular velocity of frame I itself, expressed in that same basis I plus whatever is the relative angular velocity. Okay? And that is the angular velocity of the next link relative to the current. So that will be the theta dot of that link of that joint I plus 1 into the unit vector along its z direction. That is the axis of rotation. And that angular velocity is in the frame I plus 1, that is here converted to frame I, and then added to this angular velocity of frame I itself, which is already in its own basis. This same thing, if multiplied with this matrix I plus 1 Ri, gets its expression in the next frame, which will be important because for the next value of I, this is the thing which will be sitting here. Okay, because for the next value of I plus 1 will be in the place of this. So that will be important for the conversion of the links further ahead. This is the angular velocity of frame I plus 1 expressed in frame I and expressed in frame I plus 1 itself. Linear velocity of its origin is linear velocity of the origin of the frame I itself plus this angular velocity cross the position of the origin of the next frame. Okay. And when you multiply this whole thing with this matrix, then that same expression you get in the next basis. All this 4 is for a revolute joint at joint I plus 1. Okay. If it is prismatic, then in this place theta dot will be 0, there will be a d dot, and therefore the angular velocity expressions will be simpler and more drama will be there in the linear velocity expression because there will be a relative linear velocity there. So if the joint is prismatic, then whatever is the angular velocity of frame I will be the same as angular velocity of frame I plus 1 when you express both of them in the same basis. And when you want to express the angular velocity of the frame I plus 1 in that fellow's own frame, that vector, then you have to transform this vector by this rotation matrix. In the case of the linear velocity, there will be more terms. Linear velocity of the next frame will be linear velocity of the current frame plus omega cross r, that is this term, that is omega of ith frame cross origin to origin position vector, and plus now there is a actual motion at the joint, actual linear motion along the z direction, which is the vector 0, 0, 1 into b dot, which is a scalar, converted to the previous frame in order to add it to these vectors which are already in the previous frame. Okay, and this whole thing you can multiply with this rotation transformation to get the expression in the next frame. So like this, by using I equal to 0 in frame 0, you can get motion characteristics, motion quantities of frame 1. Then by using I equal to 1, you get the same thing from I to 2 and so on. And when you go on transforming it recursively, then finally in any frame you can get the motion of any point, any frame, whichever way you want, and that will be important. For finding the actual end effector motion, it will be important just to go on putting these things with this as the position of the next origin. Okay, and finally when you go up to the origin of frame n, which is a hand frame, and through all these steps from I equal to 0 to n minus 1, you would have got the motion of the hand in the fixed base frame. Okay. For the purpose of dynamics, you will need the velocities of other points also. For example, the center of mass of each of the links. But right now, in this course, we don't do dynamics, and therefore we don't do acceleration either. So that is currently not needed. Right now, we are interested in the kinematics, motion only. So up to velocity we are going. Now, if our interest is to figure out the hand motion only, then a more synthetic direct approach also we can use. And for that, you first observe that in any mechanical system, if theta 1, theta 2, etc. are the independent position coordinates, and theta 1 dot, theta 2 dot, etc. are the corresponding independent velocities, then the velocity of any point q can be expressed as a linear combination of these independent velocity coordinates. And that makes sense because if these are the independent position coordinates, then position of any point is a function of these. So f of these things, the way at the end of position kinematics we described. And then if you want to get the derivative of that position of that point, then what do? You differentiate this function with respect to theta 1 multiply with theta 1 dot. Thus differentiate with respect to theta 2 into theta 2 dot, and so on. That is what? That is only a linear combination of theta 1 dot, theta 2 dot, etc. And the coefficients of this linear combination turn out to be those partial derivatives, which are actually here. Similar situation will hold for angular velocity also. So, taking the origin of the frame of reference n, that is the hand, as the point q, as we discussed earlier, and frame n itself as the frame of reference c, linear and angular velocities of the hand or end effector, that is link n, can be composed as linear combinations of theta dots. And linear combinations like that can be organized in this matrix vector form, where the coefficients of the linear combinations or partial derivatives for that matter appear in this matrix, which is the Jacobian of the manipulator, or alternatively you can say Jacobian of the position mapping. So you call this matrix as the manipulator Jacobian. And the entries in this will be functions of theta, because the position transformation is essentially nonlinear. However, make note that the velocity transformation is linear. That is, input velocity to output velocity. That's a linear transformation affected by a matrix, straightforward. But the entries here will be dependent on theta. That is why you can do velocity kinematics. You can start doing velocity kinematics only when positions are completely known. And if positions are completely known, then in order to evaluate the Jacobian, it is not necessary to actually differentiate. Okay, you can directly get it from this consideration. Say you want the linear velocity and angular velocity as this, right? In which the Jacobian has n columns, because here there are n velocity quantities. The derivatives of the joint variables. Now consider, if you give all the joint variables 0 rate except one, that means lock all the joints except one, IS joint, and at IS joint you give an unit input, If it is a revolute joint, then you turn that link relative to the previous one through with 1 radian per second. If it is a prismatic joint, then you move it with a rate of 1 distance unit per second. And all the other joints for j not equal to I, you give 0 input. That is lock all those joints. If you do that, then from fixed frame 0 to frame 1, 2, 3, 4, 5, 5, 6 up to, whatever, this point you have locked all the joints. This joint is free where you are giving in unit motion. That is, if it is revolute joint, then you are turning it at unit angular velocity. If it is prismatic joint, then you are moving it along the z-axis 0, 0, 1 locally, unit linear velocity. And again, all the joints after that are locked. So then what happens? Since from here to here all the joints are locked, so these fellows don't move at all. They are fixed with this. And since everything after this joint is also locked, so this whole part of the manipulator after joint I together become rigid for this particular experiment, and this entire thing rigidly together rotate or translate about or along this z-axis together, and that will be the motion of this point, linear motion of this point, and that will be this angular velocity omega cross this vector if it is revolute joint, or simply this motion if it is a prismatic joint. That will be the linear motion of this. So if it is a revolute joint, then you see omega cross this position vector, IPM, that is in this frame whatever is the position of this, and that you know because position analysis you have already done, and this direction also you know because position analysis has been done. Direction is dependent on the configuration, on the position. However, both of these vectors need to be expressed in the wave frame. Okay, that will be the linear velocity. See, this is unit vector because you are giving a unit input. So if this is the revolute joint, then this will be the motion of this point, linear motion and angular motion of this frame. That is simply the unit angular velocity. If it is a prismatic joint, then this whole thing rigidly will move in this direction with unit velocity, and that means linear motion will be this unit vector, angular motion will be 0. Okay. So this way, by taking the position vectors from this point to the hand and the unit vector 0, 0, 1 in this place and converted to this frame, you get one column of the Jacobian. Okay. So here you have given all zeros and only one. So that is why in the matrix vector product there is a linear combination of these guys in which these guys themselves are all 0 except 1. So as a result you get that particular column. So this is what you get as one column of the Jacobian. Like that you go on filling each and every column. So origin of frame 1 to here, origin and z-axis of frame 1 and this point. This much you have to do to fill the first column. Similarly, origin and the z-axis of the second joint and this point you will need to fill the second column. Like that, you go on filling the Jacobian column by column. So this is one very simple way of developing the Jacobian matrix. And then finally, you have end effector linear and angular motion as this Jacobian matrix times the vector of input velocities, joint velocities. Okay. So let us see one example, and for that, let us consider the same example for which the position analysis we have already done. And in the position analysis, we found these expressions for this 3R manipulator. And here, for a moment, you freeze your video and verify through the derivatives. That is, I am trying to develop the Jacobian. Okay. So these are the x, y, and angular position of the end effector that we developed in a previous lecture, in which C1 is cos theta 1, C12 is cos theta 1 plus theta 2, C123 is cos theta 1 plus theta 2 plus theta 3. Similarly, S means sine. Okay. So from these position equations, you try to verify these derivatives, and that will be a 1 minute break, after which we will. Okay. So I hope by now you have verified the derivatives. So x dot, y dot, phi dot we have got in this form. So this is the partial derivative with respect to theta 1. Okay. And then multiplied with theta 1 dot. So we are getting the time derivative. Similarly, components from theta 2 and theta 3. And cosine gives you minus sign, and sine gives you cosine in the derivative. And this term is free from theta 2 and theta 3. That is why this term starts from here, and this term is free from theta 3. That is why the theta 3 derivative has only the last one. Okay. Now, when you put all these as a vector, then you get this, and then these three linear combinations of theta 1 dot, theta 2 dot, theta 3 dot, you can organize in the form of this linear transformation. Okay. And taking the task space coordinates x, y, phi as the vector capital X, and the joint space coordinates theta 1, theta 2, theta 3 as the vector capital theta, their dots, their derivatives are then related through this linear transformation Jacobian, something that we derived there. Now, notice that without differentiating, how you could fill the Jacobian matrix directly for this example. So this we have already done. Now this same thing we can fill by the consideration of locking all the joints except one, which we move with unit input. So explore. This is the first link, this is the second link, this is the third link. So if we lock both the second and third links, then from here to here, all of them will become rigid together. And then the first joint we move with 1 radian per second angular motion. In that case, what will be the velocity of this point and what is the angular velocity of this hand. So the linear velocity of this point will be this joint's omega cross this vector OP, which is x, y. Okay. So that is angular velocity is unit in the k direction. Omega is this cross this position vector xi plus yj. And when you do that, the I component will be k cross j, which is minus I. So minus yi plus x j. K cross I is plus j. So that is this. Minus y plus x. These are the two components. And so minus y here and plus x here. And what is the angular velocity of this? Since from here to here all of them are rigid, then all of them together will be rotating about this point, which is the z-axis, with unit angular velocity, because that is what we are giving at this point. This. So that is 1. So when you put these three things in this, so we have got the first column of the Jacobian. Then for the second column, what you do? You give the velocity input to the first joint as 0. That means from here to here, it doesn't move. Then you give theta 2 dot as 1 and theta 3 dot as 0. So you have locked this joint also. So A, B, P together rigidly rotates about point A. Okay. The axis direction is again the same vertical that is perpendicular to this plane of the drawing. Okay. So then you have the linear motion of P as K cross AP. Okay. So that is why for the position vector, rather than xy, you get only this much, which means that out of the 3 terms, you have the later 2 terms. First term is missing, and that is why you have got this. Okay, K plus AP. So again, if you count xy from here, then whatever you would get, according to that, minus y and x will be sitting here, and angular velocity of this whole thing is same unit in the k direction. Okay. So unit, and then in the third case, you give joint motions as 0, 0 and unit here. That means from here to here does not move, and this last link rotates about point P. So here the linear velocity will be K cross BP, and that means only this fellow's x and y component get into the position vector, and its minus y and x will come here only. And for the angular motion, it is unit angular motion, so 1. So these 3 columns, J1, J2, J3, when you assemble, you get the same thing that we got earlier. So this is perhaps the simplest way to fill the Jacobian matrix and represent the velocity transformation. And once we have got this, then with the given input velocities, the output velocities, that is the hand velocities, you can directly get from here. But make note, this gives you directly the output hand velocity only, not intermediate points, not intermediate frames. So when that is of your concern, that is of your interest, then you can directly do this. Otherwise, you have to take the point of interest, and that you have to put in place of this intervector point to get this kind of matrices. And for every point and frame, you would get a matrix according to this same formulation. Now, for control purposes, quite often you will be interested in prescribing the hand motion and asking for the joint motion that is required to be given at the joints. So for that you have to solve the inverse problem. Okay, that means with this right hand side given, you have to solve this linear system of equations. And in ordinary non-redundant manipulators, for special case, it will have 3 elements here, 3 elements here. So typically we will have 6 degrees of freedom, and this matrix will be 6 by 6. For ordinary configurations, where this matrix is non-singular, full rank, there for the demanded end effector motion, you will get a unique solution for the joint motion. And as you know from the theory of linear algebra, that if this matrix is singular, then you don't know whether this system will be solvable at all or not. For general right hand side vectors, it will not be solvable. Okay, only for those right hand side vectors which fall in the range of this transformation matrix, it will be solvable, and in that case there will be infinite solutions. These issues we will consider in an example in a later lecture, and before that, in the next lecture, we study the transformation of static forces between the input actuator side and the output load side, which is the end effector, which is perhaps doing some work and encountering some external force, which it has to counter with the forces and torques at the actuations. So that static force transformation we study in the next lecture, and after that we will see the situations and try to understand the singular configurations where this matrix may be rank efficient and this mapping may turn out to be degenerate, and what may happen in those degenerate conditions, and matching the situation in the algebraic sense with the real picture that happens, that takes place for the manipulator physically. Okay, so before that we will study static force transformation, because the velocity motion mapping and the static force mapping have some very interesting similarities, and rather than similarities they have a reciprocity. Whatever happens this way for velocities, it happens that way for forces. So that we will see in the next lecture. So here we stop for this lecture.